you very much. How's everybody doing? Good conference? Yeah. So, the title of my talk is Reframing the Problem, and it's somewhat of a lightweight talk, kind of a nice refresher after some of the heavyweight ideas that have been thrown around you today. The talk has an alternative title, or a subtitle if you will, and it's called How to Think Like a Computer Scientist, which, as special as that makes me, and I'm sure us feel, really all I'm trying to say is let's learn how to think for a little bit. What I want to do is, we have an interesting career and an interesting job in that all of us here are kind of taking problems that we all, like normal people take for granted. Like, I give you a file of folders, and I need to put it in alphabetical order, and nobody really thinks about that. The filing clerk at your office is going, okay, I'm going to put it in alphabetical order, but you try and sit down and take a machine that can only look so far, that can only do so much, that needs such strict instructions. It's much more difficult. You have to sit down and think, well, how do I sort something alphabetically? You tell a kid, sort this alphabetically. Well, once he knows his ABCs, and you explain to him alphabetically means start with A and go on forward, he's pretty much done. Those instructions don't really work. And while we're all pretty good at getting really good at while we're all pretty good at giving these kind of instructions and breaking these problems down into tasks, sometimes we all hit that problem, that one wall that just kind of forces us to stop. And we're like, how do I even approach this problem? How do I even solve it? And you look at all of these computer scientists out there that are, solving these interesting problems, and you're like, how do they even get around to that? And while I don't while I don't purport to be a genius computer scientist, I am not. My academic records and will show you that I passed. And that's about it. I kind of want to explore my favorite problem. I got my degree in computer science, but raise your hand here if you have gotten a degree or are working on a degree in computer science. So really, a good number of people, but to be honest with you, not in any way, shape, or form the majority of this room. So I hope it's exploratory and interesting to those of you who have not had that level of a formal background. Those of you that have had a formal background will probably recognize the problem I'm about to discuss, but I'm about to spend 45 minutes just rehashing and going on tangents on a single thing that we spent maybe 2 weeks in my AI course in college going over, and I think it's a great example of how computer scientists have to think and ways that you can look at a harder problem and potentially come to solve it. So to start off, we're going to do a little bit of role play. So I am, let's say, I am a children's entertainer. And I do children's birthday parties, and clearly they're all really terrified, and since they don't want to pay me the cash that they promised, they hand me a lot of party favors. And I'm sure any of you who've gone to a 6th grade birthday party, or maybe even like a 4th grade birthday party knows, you tend to get a lot of these puzzles. And so, in our role play, I am this children's entertainer, and I've got just stacks and stacks of these puzzles. Some of them have got numbers, some of them have got pictures of Pokemon on them, just tons of them, and they're all jumbled up. And I really want to solve them. And because I'm rich, because the children's entertainment market is lucrative, I want to hire us to build me a system to solve all my puzzles for me. Now, this is an interesting problem, and this is kind of very indicative of what we do. I'm not asking you to take this puzzle and solve it. Because if I just asked you to do that, you take this puzzle down and you just sit down, you might jumble with it. 99% of you will probably just move it at random until you go, oh, look, this works. I totally figured that out. You just move the pieces at random. What I'm asking us to do is come up with a system that can repeatedly and reliably solve these puzzles without having seen this puzzle before. So the way we might go about and do that is we might hit Google. We might say, I want an 8 puzzle solver. We might hit GitHub and say, oh, look, there's a project. Okay, it's done. Thank you for coming to the talk. MadisonPHP, rated on Join In. But we can't exactly do that because this talk is how to think like a computer scientist. We just thought like engineers there. Engineers, I solve it, I'm done. It's been, you know, it works. Who cares? So before we really get started, to paraphrase a famous television astrophysicist and science educator, to solve our problem, we must first invent the universe. So for those of you that don't have as solid as a background, I'm going to go through your first 2 years of computer science education in a few seconds. So in computer science and in computers in general, you have a bunch of tools and building blocks. And these tools and building blocks don't make up what the computer science field is, but they are something that is used in the actual solutions. And these tools can be things like linked lists, which are a very, very basic, low level. This is literally day 2, day 1, you've learned how to turn on your computer. Day 2, you've learned a linked list. And that's a tool. And utilizing linked lists, you can make things like stacks, queues, you start making hash tables, you make state machines, trees, graphs. These are all tools that we build on and we utilize to solve the problems. Now, learning how to build a linked list, learning how to reverse a linked list in a short amount of time is a great interview question that some companies love to ask because they like to torture their interview candidates. There's something about tortoise and hare, and there's an algorithm that has that name, and I have no idea what it was. I went to the Wikipedia page once and then fell asleep and woke up the next morning. So, that's really not the important part. The important thing is knowing that I have these tools available. I have graphs, I have trees, I have stacks, I have lists, I know that sorting exists, I know that all of these different algorithms exist, but you don't necessarily have to know everything about them, just that they're available. So, now that we have the first 2 years of your computer science curriculum underway, we go back to our problem and we look at it. And so we're taking our first stab. Your project manager has walked up to you and dropped this pile of crap on your desk and said, I need this by Friday. We promised the client it would be done by then. I hope your estimate matches up to that. So we look at this and we're like, well, how do we even start to go about solving, how do we even start tackling this problem? First thing that comes to most people's heads, and I say most people's head, it comes to my head, and I assume that you guys are at least a little bit smarter than me, is the Rubik's Cube. Seems similar, right? They're both different puzzles. We know that, some guy solved the Rubik's Cube, so I wonder if maybe if I go in and investigate what happened with the Rubik's Cube, and I look at that solution, maybe I can start gleaning some information that will help me with the 8 puzzle. I mean, they're similar, right? They're both puzzles. They're both involve things out of place that have a strict set of rules to get them back into place. So we start looking at it, and all of a sudden we have all these mathematical diagrams, and you start here, and you go there, and there's like some white paper somewhere describing how all this effort that some of these crazy Russian mathematicians went through to solve this, and even if they had written their paper in English, you still wouldn't have been able to read it. And that really doesn't help us out a whole lot. And in psychology, and when you start looking at, steps and problems and barriers to problem solving and how the human brain tackles solving problems, this is actually what's known as a mental set. We're attempting to reuse a previous solution. And when it becomes a barrier, the human brain really loves to reuse existing solutions. This becomes a barrier because we're obviously taking what will be an extraordinarily inefficient solution to solve this 8 puzzle. We basically, in order to solve it, we're going to have to go back to our project manager and you can be like, I'm going to need about 8 years to go back to school and get my PhD in mathematics and study the 8 puzzles so I can come up with some sort of derived mathematical proof that I can eventually boil down into some sort of Lego Mindstorms controlled twisty bot like that one guy did on YouTube because apparently he gets paid well enough that he gets free time. So we're dealing with a mental set, and so now we go back and look at the problem, empowered, knowing that, okay, listen, we are probably getting stuck on this problem, on solving it, because I'm just trying to ram through what I already know, and I probably don't know what the solution is, so maybe we can take a step back. Something that we're all used to doing as programmers, taking a step back, abstracting out a little bit. We continue to stare at this, and at least for me, whenever the problem was first introduced, and I kind of looked at it and I was like, how in the world is my professor going to tell me how to solve this? What crazy solution is it going to be? I started hitting another barrier that happens a lot when we hit strange problems, and it's what's known as functional fixedness, which means that the brain has an extreme amount of difficulty looking at something, particularly like the 8 puzzle, and it's very difficult for it to look past the primary function. So we're staring at this puzzle, trying to think, how are we going to solve it? And all we're looking at as this physical thing that has a hole where there used to be a piece, and I have to slide pieces around, and you're looking at it very, very concretely and literally. And I know that all of you know exactly what I'm talking about, because when you start dealing with your users, you try to explain things to them, and you realize, like, click the button, and they're looking around on their keyboard for an actual button. They're looking on their jacket. You say button, they think of a physical thing. They're not looking past to the abstract notion of a button. When you say button, you're not saying something that somebody sewed on your shirt that keeps it from flying open in the wind like, some sort of Dior perfume commercial. You're talking about something that can be pressed, that is available, you can perform an action. And it's that level of abstractness that you've kind of stepped past the primary function and looked at it from a larger window. But despite the fact that we pride ourselves on being able to do that over what people outside of our industry do, we tend to still do it ourselves when we hit issues, and we come up with inefficient solutions because we can't sit there and kind of break past what is immediately available to us. So to come up with ideas for, it's kind of hard. How would we work around that? If your brain is actively sabotaging you and not making it easy for you to look past, what can we do? Well, I'd like to take a tangent for a little bit and talk about this guy. Anybody have any idea who he is based off the picture?
Eisenhower.
No, that is not Eisenhower. Yes, that is Enrico Fermi. And very, very, very famous physicist involved in the Chicago pile experiments, nuclear physicist. And he's known for a lot of different things, and I am not a physicist by far. So, if there's anybody here who has a degree in physics, they're probably geeking out over a lot of stuff that I'm not going to talk about because I don't understand. The big thing I want to talk about is one thing he was well known for doing is something that has kind of been termed as a Fermi estimation. So he was kind of famous for having, whenever they did some nuclear tests, he was standing, in the viewing platform. I can't remember how far away he was. Either way, he dropped a piece of paper when they detonated the nuclear bomb. And he basically calculated how long it took to fall and where it went. And using the calculations of how long it took to drop the piece of paper to the ground, he was able to calculate a rough estimate of the yield of the nuclear bomb. I think he calculated it at like 10 megatons, and then when they had finally done doing all the other calculations and reading all the other sensors, weeks later they came out that it was actually 20 megatons, which is scientifically very close. Scientifically, if you're off by an order, if you're off by 10 or 20 or whatever, that's, fairly close enough. It's magnitudes where you start to go, okay, something's fundamentally broken. And it's really impressive. You look at it, how can dropping a piece of paper give you any indication of how big the nuclear blast was? And so what he did with the Fermi estimations he's well known for is he sat down and he took that and he wrote down what he knew. He took down, I know that, under normal circumstances, a paper would fall this way. I know that in general, a nuclear blast is, chain reaction, going out, probably creating, a vacuum that expands, yada, yada, yada. He knows in general what's going on in there. He knows in general what's going on the paper. And he kind of has a general idea of, since I know these things, I can start to draw lines on the paper, figure out where they connect, and, theoretically, feasibly, how would one affect the other, and he can just write down a rough estimate and then just scale it outwards to what he knows to come up with a value. A more accessible version of a Fermi estimation, how many of you have ever been asked to estimate how many piano tuners there would be in Chicago in an interview? I will give you guys a few seconds to weep silently. But that problem, that little tidbit of, Microsoft interviewing wisdom is a great example of a Fermi estimation. The solution to that problem is you sit there and you say, well, I know there's, X million people in Chicago, and I know that the average household is, 2 people, and I know that the average, 50% of the households will have a piano, and I know that a piano goes out of tune after a certain amount of time, and I know a piano tuner can, tune so many pianos a day, yada, 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 and I also make some assumptions. I make an assumption that the number of piano tunes will expand, fill the market. If there's a demand for X number of piano tuners, that's probably how many there are going to be. So you figure out what the demand is, I know in general how many piano tuners there are. Great example of a Fermi estimation. And then there's the Drake equation. Has anybody heard of the Drake equation? It's an estimation of how many potentially life-habitable planets there are in the world, which gives us an estimation of how many potential planets to contain intelligent life, which of course leads to the Fermi paradox, which is we haven't seen any signs of it, so there's probably a galactic apocalypse coming our way in the next few hundred million years. So get ready for that. It's going to be exciting. So to bring it back to our problem at hand, what a Fermi estimation is in effect doing is doing what's known as reduction. And reduction is where you take a problem, you break it down, and you try to convert it into an other known solved problem. So what we've done is we've stared at this problem, we stared at this A puzzle, we're probably hitting the second week and we're getting asked, why is there no progress being made on this? And we're like, listen, I've got family to take care of, it's just, we've been staring at this, so now we're going to reduce it, because we clearly looked at it and we're like, there's no really known solution for this, we don't know about it, let's reduce it into a problem that we do know how to solve. And this is where we go back to, in particular, my sophomore year high school physics teacher, and using a technique called just write down everything you know. So if you're solving a problem and you're looking at it and I don't even know where to start, you say, don't worry about the solution. I don't know how to solve this, so let's start writing down what we do know. So we have an arbitrary game board. We know that we have a game board. We know that there's an empty piece. We know that they can be in kind of any, shuffled, jumbled up order. We know we have that. We know that I can take a piece and I can move it to another location. So let's just say, just arbitrarily, we pick the empty piece. And if we move the empty piece up, we have a new game board. And we know that what we're trying to do is we're trying to get the game board to a certain state. We're trying to get it to a solved state. We know what the solved puzzle looks like, and we're trying to get there. And I know that I can move it up here. I know that if I move it right, I create this other state. I'm looking at it. If I go back to the original and I just move that right, and I start to build out what I know, I start to kind of draw out the solution myself. How would I have done it? What can I do with it? What operations can I even do? We start to notice something. So if we go back to the very beginning of our talk and we go through our 10-second introduction to computer science, we start to see some similarities. Now that we've written down everything, what we know, we start to notice that it's looking an awful lot like this picture that we saw here. I mean, we've got, squares here, we've got points here, we've got lines, we've got scribbles next to the lines. Literally, this is the lowest brow explanation, and that's fine. That's the only explanation you need. You just know that there's a pattern, and we think, there's probably something to this. So what this is this is a graph, what I described earlier. It's a data structure wherein you have nodes that are connected to other nodes via edges. And so there are different forms of graphs. There are undirected graphs, there are weighted directed graphs. So you see right here we have numbers next to these edges, which indicate this is an undirected weighted graph. Sometimes the edges have a direction, like I can only go in this direction, but I can't go backwards. And while this is all kind of, great and whatnot, you don't necessarily have to know the finer details of what's going on. All we need to know is I know that there's graphs, and I know that there's something that uses graphs as an underlying mechanism, and that's maps. And I know that if I have a graph, which say, every point on the street map is a node, the roads or edges that connect points. And obviously, we've seen in our own experience, just using Google Maps or Apple Maps if you're brave, that we can find how to get from point A to point B. We can possibly find multiple different ways, but I can find how to get from point A to point B. That seems an awful lot like something that could be useful to us. And thankfully, there is a man named Edgar Dijkstra who spent his lifetime doing a lot of research into graphs and graph theory and finding shortest path and the direction through graphs. And so we start to think to ourselves, if this looks an awful lot like this, would it not make sense that what we use to generate the shortest path here could solve our a puzzle problem for us? If we were to able to generate each individual state as a node, and the edge being the moves that we randomly move from, we could sit there and apply the algorithms that he came up with, or some of the derivative algorithms, in particular, something that's really, really fast and powerful for it. You just apply an A-star algorithm. You've just now had your eureka moment. You sat there and you banged your forehead against this problem. You couldn't figure out what was going on. We sat there and stared at, the Rubik's Cube, and we didn't understand that either. We had no idea. We obviously didn't have access to the internet because we didn't use the Google search results. So now all we have to do is sit down and build a customized search algorithm. And we don't even have to build it ourselves. We could always go find a library or a composer or something to do it for us. Build it out, we solved the problem, we've turned it in, we've collected our money from the creepy clown that pays you money to solve puzzles that he got from kids. And we've all won. So, what did we learn? What we learned is don't fixate. As you're doing your problems, this was a very arbitrary and capricious example. That was really just a flimsy excuse to throw up a picture of me photoshopped to look like a clown. But don't fixate on your problems. Don't sit there and let functional fixedness hold you and lock you into place. There are a lot of different things you're dealing with that may not be as high-minded and computer science-y as sitting there and solving an 8 puzzle. But one example of a project that I've been working on, I have potential input that actually comes out of an OCR engine, and I'm trying to find the final sum in this OCR report. And the final sum on every single report is the words, grand total, colon, and then there's a number to it. And I sat there, and that portion of the report, that portion of the code kept failing on many different reports because of failures in the OCR scan. And I sat here and I started building larger and larger regular expressions to take care of all these random edge cases. Like sometimes the colon wouldn't show up, sometimes it would show up as a semicolon, sometimes it would show up as a backtick. Because God knows why you would think that a colon was a backtick, but it happens, and you got to account for it. And then some other lines, as my regular expression got larger, it started becoming, the regular expression started misfiring on other lines because it was so loose, accounting for so many different situations, that I wasn't able to do anything. Taking a step back, loosening my fixation on, I see a string, I'm trying to find something in the string, so let me apply a regular expression to it. Loosening the mental fixation, I was able to sit there and I came up with something significantly more flexible, which is, since I'm trying to split the string, and I don't know where to split the string because the word could be misspelled, the colon could be missing, I sat there and I just did something incredibly stupid. I just split the string on all the spaces, and I kept popping off the top of the stack into a new string, and as soon as I found something that was close enough to what I was looking for, I just took everything else. I stopped treating it like it was a string I could apply a regular expression to, and I came up with something that was more flexible and not misfiring on every other line. Just not fixating, taking a step back and saying, maybe this is not a string, maybe this is just something a little bit more malleable, maybe it's water I can pour into another cup, and just wait until I reach the point that I need to get to. Which leads to pulling back and abstracting. Making sure to remind yourself, we kind of forget sometimes that we can do this. We're so used to doing our programming. just a reminder to yourself to, as you're working on a problem, to really think about it more abstractly. When we came up with the solution for solving an egg puzzle, if I had started out this presentation and showed you the egg puzzle and said the same algorithm that got you the driving directions to this hotel is the same algorithm that gives you the solution to the egg puzzle, you would have looked at me like I was crazy. It doesn't make sense. One's a puzzle, one's a map on the ground. What is the relation of the two? Very, very, very little until you actually pull back from what it actually is and look at it abstractly. The different pieces that make up the problem. Which leads to the practical thing of something that a lot of people forget about that is very helpful, is just write everything down that you know. If you're hitting a problem that you can't seem to solve, if you're struggling against something, stop trying to solve it, stop trying to figure it out. Write down everything you know, no matter how irrelevant, how unrelated it sounds, and just get it out there on paper in front of you. Your brain is probably the most advanced pattern matching system in existence that we know of. Get it in front of you. You'll be surprised what starts to jump out of the page at you. You'll start to find smaller subcomponents of the problem you're trying to solve looks very familiar. And you can go, oh, well, I can take this out of the picture and reduce the scope of the problem and just focus on solving something smaller and farm out the things that I already know how to do. And if all else fails, just Google. We are engineers after all. We just want to think like computer scientists. So, thank you for listening. I want to remind you all to please rate your talks on Joined In. Please rate my talk on Joined In. I hope you enjoyed it. And then for those of you who might be in the Chicago area, next weekend we're having a conference that takes place entirely in the line to hot dogs, waiting on some delicious hot dogs. Thank you very much.